Hello, this is Dr. Hanaa Assil and this is Unit 3, October 2024 in the Pearson Edexcel International A-Level Chemistry. So let's take a look at the questions. The first question here was, solutions of 3 group 2 chlorides were treated with solutions containing different anions. So here we're talking about group 2. And we're talking about reactions with sodium hydroxide, with carbonate, with sulfate, and which group 2 ions will give a precipitate or no precipitate. First of all, you should remember the one that gives a precipitate with sulfate. We have X has a white precipitate with sodium carbonate and with sodium sulfate. That means the one that gives a white precipitate with sulfate is the barium ion. So first of all, X is the barium ion, and we should keep in mind the trend in the solubility of the different compounds of group 2. Remember that if we're talking about carbonate, sulfate, or nitrates, as we go down group 2, the cation is larger, so less polarizing ability. So when we're talking about carbonates or sulfates of group 2, the one with magnesium is more soluble than the one with calcium or barium. So remember that as we go down group 2, the carbonates become less soluble and sulfates become less soluble. But if we're talking about hydroxides, so the cation with hydroxide, the hydroxide, if the cation is small, that is less soluble. Hydroxides with magnesium will be less soluble than with barium or calcium. So looking at this table, X is something that with hydroxide, it doesn't form a precipitate. With carbonate and sulfates, it forms a precipitate, so it has to be down in the group 2. So X is probably barium, because barium gives precipitates with sulfates and with carbonates. Now Y gave a precipitate with the hydroxide, and we said if we're looking at group 2, the one on top, hydroxides will be less soluble. So if we have a white precipitate with the hydroxide but not sulfate, for example, then this is probably magnesium ions. Now, Z gave a white precipitate carbonate, partial white precipitates with the other, so it is something that is above barium. So if we say X is barium, Z is probably calcium, or it could be strontium. Based on that, we're asked to do flame tests to confirm the identity of the cations. Complete the table to show a possible identity for X, Y, and Z and the colors of the flame tests produced by each cation. You are required to know the flame tests for all of these. Now, we said that calcium, X was barium. So if X is barium, what color of flame test should we see? With barium, it should be green. Now, we said that Y was magnesium. Now, if we do a flame test for magnesium, you should remember magnesium gives no color. Don't say white, we say no color. And then we said Z is either calcium or strontium. So if we say it's calcium, in the flame test, it gives a brick red color. Describe how the presence of chloride ions can be identified and confirmed. Remember, what is the test for chloride ions? Add dilute nitric acid, then aqueous silver nitrate with chloride, it gives a white precipitate. Bromide, cream. Iodide, yellow. We're talking about chloride, so it should give a white precipitate. Now, how is it confirmed? We said this white precipitate is soluble in dilute ammonia. Describe in outline an experiment to compare the thermal stability of group 2 carbonates. If we want to know the thermal stability or compare the thermal stability of group 2 carbonates, usually what we do is we heat the carbonate, pass the gas. Of course, if we're heating a carbonate, it should give carbon dioxide gas. So pass the gas through a specific amount of lime water, and the one that causes the lime water to become milky first is the one that is less stable. So this is how we do the experiment. We should weigh, if we're comparing between several carbonates, then we weigh equal masses of the carbonates, put into boiling tubes, put equal volumes of lime water in a test tube connected to the boiling tube, heat with the Bunsen burner at the same distance. So you can say that the boiling tube was fixed at a certain distance above the Bunsen burner. Use a stopwatch to determine the time taken for the lime water to be cloudy, and we should see that the one that takes less time, that means it turns the lime water milky faster, then it is less thermally stable, or it breaks up more easily. Give a reason why the experiment described may not produce the expected results for all group 2 carbonates. Remember, we said as we go down the group, the carbonates become more thermally stable, so they need heat for longer time, a higher temperature to break up. Well, if we do that in the laboratory, then the Bunsen burner flame may not be hot enough to cause decomposition of the salt. Again, remember that we said as we go down group 2, carbonates, sulfates, nitrates become more stable, so we need to heat it to a very high temperature in order to break it up. And if we're asked why, you should remember that a small cation with high charge like magnesium has more polarizing ability, and therefore it distorts the cloud around the carbonate, breaking the CO bond more easily. Okay, question 2 says a student carried out an experiment to find the enthalpy change of neutralization between a solution of sodium hydroxide and hydrochloric acid. 25 centimeter cubed of sodium hydroxide solution was pipetted into a polystyrene cup. 5 centimeter cube portions of 2 mole per decimeter cubed hydrochloric acid were added at regular intervals. Maximum temperature of the reaction mixture measured after each addition. So we have this graph, and we are told to draw 2 lines of best fit to determine the maximum temperature change at the point of neutralization. Now, this is very important. This graph is not really 2 straight lines. One of them is a curve and the other is a straight line. So this is actually how we should join them. And then at the point where they intersect, that is where we take the volume and the temperature. So in this case, the volume was 22.0 and the maximum temperature was 25.2, but we want the change, the maximum temperature change. So notice that we started at what? 17.5 to 25.2. The temperature change is 7.7 degrees Celsius. Calculate the concentration of sodium hydroxide solution using an answer from A1 and information from the procedure. So what do we have? We are told that we have 25 centimeter cubed of sodium hydroxide, and we added portions and measured the temperature, and we find that the volume, the total volume of HCl added was 22. So I can get, first of all, I can get the number of moles of HCl. Concentration of HCl, we're given up there, is 2 mole per decimeter cubed, times the volume over 1,000. This gives the number of moles of HCl. Then, if we look at the equation, this is the balanced equation, and obviously we relate the number of moles. The number of moles of HCl is the same as the number of moles of sodium hydroxide. So we're required to get concentration of sodium hydroxide. Well, you should know concentration is number of moles over volume. The volume of sodium hydroxide was 25 centimeter cubed. So we need to divide by 1,000 to put into the equation. So this is the concentration of sodium hydroxide. Calculate the enthalpy change of neutralization in kilojoule per mole. So we're required to get delta H. How do we get delta H? You should realize that we get delta H using Q is equal to MC delta T. Now what is M? Look at the information. We put 25 centimeter cubed of sodium hydroxide, and we used a total volume of 22. That means my M is the total of that. Now, what is delta T? Delta T we got from the graph is 7.7. So, calculating Q, M, C, delta T, of course, C is 4.18. This gives me the quantity of energy in joules. We divide by 1,000 to work in kilojoules. Then we need delta H, and we should know that delta H is Q over N. So what is N? The number of moles that we calculated was 0.044. That was the number of moles of the sodium hydroxide, which is the same as the number of moles of water. And we get this value in kilojoule per mole. Have we finished? You have to remember that delta H must have a sign, and the question always says include a sign. What is the sign? Well, obviously the temperature went up from 17.5 to 25. So going up means the reaction is exothermic, and that means the delta H must have a negative value. The published value for the enthalpy change of neutralization is minus 55.84. Our value is obviously less. Give 2 reasons why maximum temperature is not reached in this experiment. First of all, we're told that the procedure does not allow the maximum possible temperature to be reached, and that's why we got the maximum temperature from the graph. So why is that? Well, first of all, heat loss to the environment, and probably another reason why we did not get the correct maximum temperature was probably the solution was not stirred. Give an improvement to the experimental method that will increase the accuracy of the titer value. Of course, if we are adding regular intervals maximum to reach 5 centimeter cube portions at regular intervals, well, that allows more loss of heat to the environment. If we add the required amount in one portion to the end point, this would allow less loss of heat to the surroundings. Give an improvement to the experimental method that will increase the accuracy of the calculated enthalpy change of neutralization. How can I get a better value for delta H of neutralization? Well, what did he do? He had the polystyrene cup and he was adding portions. Well, one method would be add a lid to the polystyrene cup. Again, that would reduce heat loss. Question 3 says, a student purified a sample of an organic liquid by distillation. Draw a label diagram of the distillation apparatus, including a thermometer. Please practice drawing this kind of apparatus in which we have the flask with a thermometer in it, and the bulb of the thermometer is near the entrance to the condenser. Remember, the condenser is a tube with a jacket around it in which the cold water goes in from down and goes out from the top, and then you should have some sort of a receiver container, whether a conical flask or a beaker. The purified product was treated with a small volume of bromine water and shaken. The bromine water was not decolorized. What is the most likely conclusion about that? Remember, bromine water is test for what? It's test for presence of a double bond or presence of alkenes. So if the bromine water does not change from orange to colorless, then we do not have any alkene, or we do not have C double bond C. The purified product was also treated with Fehling's reagent. No color change was observed. Again, Fehling's reagent is a test for what? Remember, this is a test for aldehyde. So if we have aldehyde, the blue color of the Fehling should change to brick red precipitate. But if there is no color change, that means no aldehyde. The purified organic liquid was refluxed with acidified potassium dichromate. A color change was observed while refluxing. The resulting solution was distilled. The student concluded that the final product must be a ketone. Discuss why the student is incorrect using all the information above and giving an alternative identity for the final product. So we're saying that this liquid was refluxed with potassium dichromate, and that means it was heated under reflux in an apparatus that looks like this. And we're told that while it was being heated potassium dichromate, the color changed. That means that the original liquid that we were trying to purify was something that can be oxidized by potassium dichromate. Now, the student said it must be, the final product must be a ketone. Well, what do we know? We know that if I'm starting with a primary alcohol, so if my original organic liquid is a primary alcohol, it can be oxidized to give an aldehyde and eventually an acid. If it were a secondary alcohol, it can be oxidized so that the final product is a ketone. So the fact that the final product must be a ketone, no, it's a ketone only if the purified organic liquid was a secondary alcohol. Of course, if we're starting the organic liquid as a ketone or as a tertiary alcohol, it will not be oxidized. It cannot react with potassium dichromate. So the final conclusion is, okay, so the original liquid was oxidized, so that original liquid cannot be a ketone or a tertiary alcohol. The final product, the student said the final product must be a ketone. No, it's a ketone only if the original liquid was a secondary alcohol. If it were a primary alcohol, then I would end up with an aldehyde or eventually, under reflux, a carboxylic acid. Explain how information easily obtained from the distillation experiment could be used to confirm the identity of the final product. So we were distilling our compound. How can we know the identity? Well, look at the thermometer, the boiling point, the temperature at which the liquid is being collected. We can determine it from the thermometer compared to data book value, and this can be used to identify the product that was being collected. Hydrogen peroxide slowly decomposes to form oxygen and water. Many different compounds can act as catalysts for the reaction. In order to compare the catalytic effect of different compounds, an experiment was carried out by a student. So, 0.5 grams of each solid catalyst powder and a drop of washing up liquid that were added to separate 50 centimeter cube measuring cylinders. 20 centimeter cube of hydrogen peroxide was then added to each measuring cylinder. At 30-second intervals, the volume reached by the foam was recorded. Of course, the hydrogen peroxide, when it decomposes, we are told it gives oxygen and water. Now, this oxygen gas that is bubbling with the washing up liquid will form a foam. So, the faster the foam is formed, or the higher the volume of the foam, the better the catalyst. So, we have these results with 3 different catalysts, and we're told first to label the axis of the graph. So if we're trying to measure rate, what are we measuring? Time in seconds on the x-axis and the volume of H2O2 and foam per centimeter cubed on the y-axis. State how lead oxide can be identified as the best catalyst. So looking at the graph, which one was the best catalyst? Well, the one in which the graph was steeper. So the curve was the steepest with lead oxide, so that means that that was the best catalyst. Calculate the maximum rate of foam production measured for lead oxide. So what was the rate for lead oxide? Remember, to measure the rate, we draw a tangent, so that blue line is our tangent, and we measure the distance, the difference in y over the difference in x. That would give us the slope, which would give us the rate. So the slope of that curve at the he wants the maximum rate, so we draw the tangent at the highest or the steepest point in that graph. So this comes out to a slope of 0.6 centimeter cubed per second. So just why the value calculated from the graph may not be accurate? Well, let's look at the graph. This is difficult because we did not take enough readings for each. Remember, each curve, it was made from what? 4 points or 5 points. We need more readings to be taken in order to have the extrapolation to be more accurate. In most kinetic experiments, the rate of reaction decreases with time. So just a reason why the rate of reaction seems to increase in this experiment. So with time, the rate seems to increase for all of them. So when we have the rate of a reaction increasing like this, the most probable reason is the reaction itself is exothermic. It is giving out heat, and the increase in temperature causes the increase in rate of the reaction. Otherwise, the rate should be slowing down as the reactants are being used up. In a repeat experiment, a larger measuring cylinder was used so that it contained all the foam produced. Sketch the expected graph of the volume reached by the foam until the reaction is complete using manganese dioxide. So where is the graph for manganese dioxide? Can you see the graph for manganese dioxide? It starts off slow and then it speeds up. If we're following it till the end, then the graph should eventually flatten out because no more H2, no more reaction is occurring. Hydrogen peroxide is corrosive. Draw the hazard symbol that should be displayed on the bottle of hydrogen peroxide. If something is corrosive, you should know that this would be the symbol for corrosive. Please learn the symbols for the hazard symbols, and learn to draw them. So in previous exams, they've asked to draw certain hazard symbols such as flammable. Here we're drawing corrosive and so on. State one safety precaution that should be taken when using hydrogen peroxide other than wearing a lab coat and safety spectacles. If I'm working with something that is corrosive, what safety precaution should I use? Of course, we should wear gloves when working with anything that is corrosive. The risk of harm to students needs to be reduced before they carry out this experiment in class. So just another control measure to reduce the risk for students. So we're saying wear gloves. What else can we do? If we're saying that the hydrogen peroxide is corrosive, then another method of reducing the risk would be dilute the solution or add water to the hydrogen peroxide so that the solution is not too concentrated, so that there is less risk due to the fact that it is corrosive. Give a reason why during the experiment the measuring cylinders should be placed in a tray. So he was saying the measuring cylinder is placed in a tray. Of course, if the foam is too much and it spills over, then having it in a tray is much better to collect any spills of foam or to allow the spills to be cleaned easily. So that's the end of this exam. I hope this was useful to you, and good luck in your exam. Thank you.